Let's fully go through an example of a one-variable chi-squared test using the example data we used previously of number of people reporting a motor vehicle accident by season. Our research question of interest would be, does the distribution of people reporting motor vehicle accidents differ by season? In other words, are motor vehicle accidents equally distributed by season? As we mentioned before, our null hypothesis, or H0, will be there is an equal distribution of motor vehicle accidents by season, which we will write as P1, or the population proportion in our first season, equals P2 equals P3 equals P4 equals 1 over 4, or 0.25, since we have 4 groups and we are assuming with the null that they are equally distributed within those 4 groups. The alternative, or H1, will be that the null is false. Our third step will be determining a decision rule. In this case, I am interested in testing using an alpha level of 0.01. We can also find our degrees of freedom, for which the formula is degrees of freedom equals the number of categories of our variable, or C, minus 1. We had 4 categories of our variable of interest of season, so our degrees of freedom is 4 minus 1, which is equal to 3. Let's now find our test statistic. As I mentioned, I like to use a table to arrange each of the steps of the calculations in order as we're going through. We'll first start with our observed frequencies, or our observed number of people reporting motor vehicle accidents, which will just be the observations that we have in each season. Our expected frequencies we will find using our formula of the expected proportions in each category based off our null times our sample size. In this case, our expected proportion in each group was 0.25 times our sample size of 200 will get us an expected frequency in each one of our groups of 50. I have written the expected frequencies of each category that we just calculated in the associated column in our table. We will then move on to our next step of finding the difference between our observed and our expected values by subtracting the observed minus the expected, which will get us -10, -14, 28, and -4. We will then square each of these values. -10 squared will get me 100, -14 squared will give me 196, 28 squared will get me 784, and -4 squared will get me 16. We will then divide each of these values by their respective expected frequencies. 100 divided by its expected frequency of 50 will get us 2. 196 divided by its expected frequency of 50 will get us 3.92. 784 divided by its expected frequency of 50 will get us 15.68. And 16 divided by its expected frequency of 50 will get us 0.32. Adding each of these values together to find the sum will get us our chi-squared statistic of 21.92. If you had conducted your one-variable chi-squared test in SPSS, it would have given you the test statistic that we found of 21.92 and an associated p-value of less than 0.001. Our last 2 steps in our hypothesis test will be making a decision about the null hypothesis and interpreting our decision. Since our p-value of less than 0.001 is less than our chosen alpha level of 0.01, we would choose to reject the null hypothesis. Our test results would be considered statistically significant. When interpreting our decision, since we rejected the null hypothesis, we will say that we have enough evidence to conclude that the distribution of reported motor vehicle accidents does not appear to be equally distributed by season. In other words, there does appear to be a difference in the distribution of reported motor vehicle accidents by season.